If you were to look down on Earth from space, you would notice that the illumination is consistent across the entire surface. As a result of the fact that the Southern Hemisphere contains a disproportionately large area of dark ocean waters, we might expect the situation to be inverted when viewed from sea level. Scientists have been fascinated by this phenomenon ever since we were able to launch satellites in the early 1970s and measure albedo, the amount of solar energy that is reflected into space. There is a possibility that the riddle has been solved at this point. The reason for this is that even though the oceans in the Southern Hemisphere take in more sunlight than those in the Northern Hemisphere, the Southern Hemisphere also experiences more storms. The clouds that form during these storms act as reflectors, which reduce the amount of solar radiation that is reflected into space. According to Yohai Kaspi, a geophysicist from the Weizmann Institute of Science in Israel, the new discovery addresses a core scientific puzzle and enriches our understanding of Earth's radiation balance and its effectors. Despite the fact that albedo is influenced by a number of factors, such as whether or not there is snow on the ground, measurements were taken closer to the surface of the Earth revealed that there is a difference in albedo between the two hemispheres. When viewed from a greater distance, however, Earth does not appear to have this feature. The researchers gathered data from a variety of sources, such as the ERA-5 Global Weather Dataset and the NASA Terra satellite, both of which include satellite measurements in their respective datasets. They compared the data on cloud cover over the past half-century with the information on the locations and intensities of storms. The rebalancing of the albedo was demonstrated by the researchers by observing the patterns of cloud-generating cyclones and cloud-suppressing anticyclones that were created in the atmosphere as a result of the interaction between temperature and pressure. Yohai Kaspi, a climate scientist at the Weizmann Institute of Science, explains that the hemispheres continue to maintain their symmetrical shape as a result of the cloud albedo that is produced by intense storms in the Southern Hemisphere. This demonstrates that storms are the connecting factor between the brightness of the surface and the brightness of the clouds, which explains the asymmetry puzzle. The next question that needs to be answered is how the heat brought on by climate change could throw off this equilibrium. The models of climate change suggest that as the Earth warms, there will be a reduction in the number of storms as well as their intensity in the Northern Hemisphere, whereas, in the Southern Hemisphere, these reductions are expected to be more gradual. On the other hand, the phenomenon known as Arctic amplification, which describes the knock-on effects of fast warming near the North Pole, is forecasted to increase the number of severe storms in the Southern Hemisphere. As a direct consequence of this, the albedo symmetry will most likely be disrupted. According to the data, the cloud levels in the Southern Hemisphere become saturated during intense storms. This suggests that more extreme weather events may not lead to increased cloud albedo in that region. It is possible that the albedo of the oceans in both hemispheres is decreasing at the same rate due to the fact that storms in the Southern Hemisphere tend to be more intense than storms in the Northern Hemisphere, even though there are fewer storms overall. At this point in time, the future of the radiance of the Earth is unknown. According to Kaspi, it is too soon to tell if the symmetry will be broken as a result of global warming. As global warming continues, finding solutions that involve geoengineering will become an increasingly important part of trying to preserve human existence. It is essential to have a solid understanding of fundamental climatic processes like the symmetry of the hemisphere's albedo in order to discover effective solutions.